Hello everyone and welcome to a longer form video where I'm going to talk about my journey implementing Visual Slam from scratch. And my goal today is to sort of share some insights, share some resources, and then talk a little bit about my own implementation. So if any of you are interested in listening or like want a deeper dive into this topic, then this is the video. So I built Visual Slam from scratch because I was actually working on this video called I Rebuilt the Vision OS from scratch. And the main thing that I focused on in this video was essentially getting Visual Slam working. So I implemented both aspects of the front end, so that's visual geometry, and then the back end, so actually doing the graph optimization. So I tried to get both aspects implemented. Now I did fall short in implementing graph optimization by the end of this video. I had some issues with my graph optimization. So I didn't get it fully working, just as a disclaimer. So it's also a call for help if anyone actually wants to see, but essentially my Visual Slam is a work in progress, but I just wanted to make this video. Hopefully it's helpful to some people because I've made videos in the past and people reach out to me, ask me like about X, Y, and Z. So maybe this video can help clarify things because writing Visual Slam from scratch, it's fun, I guess, in the sense that you get to learn a lot, but it's really hard and challenging, which actually makes it fun, right? Because if you do easy things, like that's not fun. So where do we even begin? Well, let me tell you guys about how I approached learning Visual Slam from scratch. So just a bit of background. I'm in university. I take software engineering as my major. So I have like some background in programming, but in terms of like robotics, I've only mostly just used Visual Slam or Slam in the past, and not even Visual Slam, just Slam with a LiDAR for like my racing RC car. So coming to this project, like I really didn't know how Slam was working under the hood. So my goal by doing this project actually was wanting to understand how Slam under the hood works, because I felt that Slam is such a technology that's like used in a lot of places, right? So you see it in robotics and you see it in VRs, used in VR technology. So it feels like it's used in a lot of places. So I felt like it was important to understand how it was working under the hood, and what better way to learn how it works under the hood than to build it. Am I correct? So that's really how my journey began. And I started this like journey around a year ago, or not, a bit less than a year ago. And at first it was really overwhelming, right? Because like where do you even get started? So I'm going to point out some resources right now and tell you guys about the things that were the most helpful to me. And I'll make a first disclaimer, which is that Slam is very broad. All right, there's a lot of different ways to implement it. And today I'm just going to be focusing on Visual Slam. So that is using a camera to figure out to do the slamming as opposed to a LiDAR. So, I mean, a lot of the ideas are very similar, especially the graph optimization part. But I haven't tried doing it with a LiDAR, doing LiDAR-based Slam. So I will not comment on how to do it because I don't know how hard it is. So from a camera-based Slam perspective, if you want to learn how that works, I would recommend, so I actually put it in, if you go to my GitHub and there's this repository, so this is actually where I implement my Slam. I link, the first two links were the most helpful to me. So number one is this textbook called Slam Book Yen, or like Slam Book in English. It's like written in Chinese, but they translated it in English. And this was sort of my Bible for Slam. And it covers sort of the fundamentals of how do you go from nothing to a somewhat working Slam algorithm. So they talk, if you look at the outline, first they give you some fundamental knowledge. So I read up on most of these chapters. I think the only one that wasn't any useful to me was like Lie algebra and Lie groups. I know it's important, but I didn't really, apart from like understanding what SL3 and SE3 is, the rest, like derivations, it wasn't directly useful to me. But the rest, like understanding the basics of nonlinear optimization. At first I saw there's a bunch of equations, right? Like Gauss-Newton, first and second order method. Like at first it's not very apparent to you why you need to understand nonlinear optimization. But as you get into the Slam, the actual Slam technology, So visual geometry here, they have, when they do solving PNP through optimization by G2O, that's why you actually need, or actually, sorry, 3D to 2D, solving PNP by minimizing the reprojection error. Actually implementing that is essentially doing nonlinear least squares, in which case I use G2O for that part. So all that to say that there's all these chapters, basically all the ideas here, every single chapter, I sort of use these up to chapter, say, so I didn't do Dent's direct method for visual geometry. So I used chapter 6, not chapter 7. Chapter 8, definitely bundle adjustments. And some ideas in chapter 9 I started implementing, like post-graph optimization or like a sliding window. And then chapter 10 with loop closure, I also tried implementing that. And then dense reconstruction, I didn't worry about that part because for me, SLAM was just like the main focus is to get the pose of the camera and not, didn't really care about like mapping and creating a dense map. So I didn't worry too much about this chapter. But yeah, there's like all of these chapters were really helpful to me. So as I worked on my SLAM, the way I think everyone has a different learning style, obviously, right? But for me, I sort of jumped back and forth. I would do some implementation, and then if there were ideas I was like feeling lost, then I would revisit the books. But I'd say at first, really, chapter 1 and 2, actually chapter 1, like the formulation's kind of nice, but I don't think it's really necessary or like fundamental. I think to understand what SLAM is about, you should probably revisit chapter 1. But chapter 2, quaternions, transformations, oh my god, this is not only fundamental for SLAM, but if you're going to go into robotics, you need to understand how these work. What are quaternions? What are the different ways to represent orientations? What are the different ways, like when your camera moves around from one position to the other position, how do you represent that, right? So the position is a it's in 3D, right? So it's X, Y, and Z. But then to make your life easier, you want to use homogeneous coordinates because then you can use a 4x4 transformation matrix to multiply it with the orientation. And then there's the rotation matrix, right? So these ideas are really important, and you need to make sure you understand that correctly. Because when you go and actually implement SLAM, right? How do you actually encode the position and the orientation of the camera? Like there are different ways to go about it, right? And if you don't even have an idea of what are different ways to represent your motion, then you'd be really lost. So this is a really fundamental chapter, right? Now, already I feel like I'm already overwhelming you a little bit, but one key piece of advice I would give here is that you really want to work on one piece at a time, right? So when I started SLAM, oh my God, it was so overwhelming because you see all these words. When I started this project, I didn't know what a quaternion was. I didn't know what a rotation matrix was. Or maybe, yeah, I might have had a very faint idea of these concepts, but I didn't fully understand any of these. And so it was really overwhelming. And what got me through was one, I did things in chunks, right? So when I started to implement SLAM, I focused first on just doing visual geometry, which is just taking 2 consecutive images and trying to infer the motion of your camera based on that. So not doing any of the fancy mapping, right? So if I give you 2 images and I ask you to figure out, okay, what's the movement what's the relative movement based on these 2 images, you can try and figure that out by minimizing the reprojection error. So they actually talk about here in chapter 6 about the 3 different methods you can do from 2D to 2D, 3D to 2D, or 2D to 3D. And I have this sort of implemented here in visual VO here, which stands for visual geometry. So this was my attempt at implementing visual geometry. And this is I'm actually relatively happy with my implementation here. It's relatively clean. So you just process your frame and then you can select which method you want. So in general, right, like the high level, you convert your image to grayscale. You have, in my case, you compute a depth image if needed, and you can solve for your camera motion. So you do, before you solve for your camera motion, you need to match your key points across frames. So there's this matching, and then depending on what method you use, for 2D to 2D, we use epipolar geometry. For 3D to 2D, we minimize the reprojection error. And for 3D to 3D, you do ICP, which I have not implemented. And then at the end of it, you get a transformation. So this is a transform, which tells you the relative orientation and the relative translation of the camera. And that is essentially visual odometry. So this was relatively trivial to implement if you know what you're doing, right? Of course, I didn't know what I was doing at the time, but I found it to be a really, really good exercise. Now you'll notice that I implemented it in Python. And if I have an advice, it would be actually to implement it in Python as well, just to make your life easier. Now you won't get the best performance if you really want it for performance. And if you look at modern day like OrbSlam, which is the most popular implementation of Slam out there for visual Slam, you'll notice that it's in C++. And you use C++ because it's much faster than Python, right? Python runs each code. It's an interpreted language, so it will just run each line of code on the fly, as opposed to pre-building the code into some binary, into zeros and ones already. And C++ is just so much more efficient than Python. But the reason Python is a lot easier to work with is because of its debugger. Like literally I can set a breakpoint in Python and I can run my code. Like I can set a breakpoint here and then I run my VS Code debugger and it would just stop there, right? In C++ you can do that too, but you need to recompile your code every single time. And you have to use something like GDB or LLDB with the Mac. And it's just a lot more tedious. But if you're trying to create production ready code, of course you need to go for C++ because you can write super buggy code in Python and not realize it. And in the long run, you will shoot yourself in the foot. But the reason I actually started this project in C++. So actually, if we go here, so the original repository was in C++, and I implemented visual odometry here as well. However, it was so very difficult to debug. I made a big mistake here where I prematurely optimized by using the VPI library, which is written by NVIDIA. And because I wanted for Slam to run in real time, like you need hardware acceleration. So one thing that takes a long time is detecting the features and matching these across frames. So you can speed this up by using a hardware accelerated implementation. Except that once you get into that territory, it gets really hard to debug if something goes wrong. And in Open with the VPI library, you need to worry about memory, and you need to reason about memory because if you, let's see here, image format converter, there are essentially different formats that these images can be stored in. So if you just take a PNG image and you load it in OpenCV, I believe the default is just each pixel is, if it's an RGB, it has 3 channels and it's 0 to 255 for each channel, right? But if now you're working with a different format, if we're computing the disparity, so you want a depth image, right? Each pixel stores the depth value, in which case you have a slightly different format. Also, there's the way memory works, generally you want things to be byte aligned or memory aligned, and since we generally work with 32-bit or 64-bit systems, generally it's much better to have things stored at 4 bytes in intervals of 4 bytes instead of 3 bytes or 6 bytes, right? You want things to be byte aligned or memory aligned. So therefore, generally, when you store images, you actually store you pad it with the 4th byte so that everything is memory aligned. And when you load it into memory, it's much faster. Anyways, this is like a rabbit hole that I went into. But I think you need to come back. I got into this rabbit hole and I realized that what am I doing here? Like, why am I prematurely optimizing when really my goal with this project was to understand how Slam works, right? I want to understand how Slam works. And so why am I worrying about performance so much right now when I can't even get my basic visual odometry to work? And so when I was implementing my main computing, let me see here, run Z visual odometry, I had a lot of trouble. I had a lot of trouble debugging when I was minimizing the reprojection error and why that wasn't working. like the transform was incorrect, I had a lot of trouble figuring that out. And actually, no, that wasn't the reason. Even before that, when I was trying to compute the depth image from the disparity image, I had issues with the format, and I could not debug it for the life of me. And so I was like, if I'm having so much trouble right now just debugging this trivial issue that it seems to me, I'm never gonna finish this project. And so therefore I decided to switch over to Python. Okay, so that's my first piece of advice. There's the textbook, and we have do it in Python is what I would say. You will lose out on some of the performance, but I think it's a worthwhile endeavor. You'll save some time for sure. Now, there's another resource that I will highly recommend, which is this lecture series by Cyril Stackness. This is a bit more in depth than the book itself, and I actually started with this video series as opposed to the book because I met someone at Hackathon. I told him I wanted to do Slam from scratch, and this was like the series that he recommended me, and he actually went through everything. I went through most of it, and it's helpful. It's quite in depth, but sometimes it's more than what I needed. Well, so if you really want the depth, I would recommend these videos, but sometimes you also forget, right? So it's I think hit or miss for some of these. I would recommend the camera basics and propagation of light is really good. This really helped me understand, okay, how do you go from a 3D object and to an image, right? Because when you're minimizing the UV projection error, you're essentially projecting a 3D. You're projecting your 3D landmark in 2D, and then you'll have a feature, right? So how that mapping works, you need to understand that. So that's why I would recommend this video, camera basics and propagation of light. Things like key points and descriptors, these are also really important. So I would recommend these as well. All right, so I think those are the main two resources, the book and, let me see, let's go back here, the book and the lecture series. I also mentioned some other implementations here, but when I was implementing this from scratch, I tried as much as possible not to look at other people's implementation, just because I wanted to I wanted to make the design decision myself. I didn't really want to copy what other people did. And so I think that's a really good way to learn. And once you implement it yourself, you can then look at how other people implemented it and see, why did it implement this way? Is it better? And were my decisions better than what he did, right? So if you directly copy someone else's implementation, you won't sort of have those ideas of what could he have done otherwise, and why didn't he make those decisions? Whereas if you have to implement it yourself from scratch, you are already faced with all those decisions, and then you'll have to choose the best one, right? And then you can later on you know why you made those design decisions, as opposed to just copying someone else's. And that's also the reason why you would make your own implementation as opposed to using someone else's implementation, right? And it just depends on, what do you care about? What problem do you care about solving? And for the problems that you don't care about solving, you can use a library, right? So for example, like detecting features and matching them, I could have also implemented my own I could have made my own implementation, but I didn't care that much at that level of abstraction to detect the orb features. Like that's too much. You can just use OpenCV. So even when I say from scratch, what does from scratch mean, right? Because like from scratch could mean, oh, I did Slam from scratch. I didn't for my VR headset, I didn't just use an API. I actually cloned the code and built it. So it's from scratch. Or you can say I wrote my own implementation, but I used some libraries under the hood. Or you could say, oh, I fully did it from scratch, in which case that would take years, I think, because the writing orb. I mean, orb is not trivial to implement orb detectors. So all that to say, these are the two most helpful resources, and I'm rambling a little bit. And this is my own implementation. So I have visual geometry implemented, and then visual geometry gets me to around 14 centimeters of error. And that wasn't good enough for a VR application. It might be for, if you're driving a car or something, but for VR applications, you need at least like within centimeter precision, because you can really tell the difference when you're moving your head around. So that's when I was like, damn, okay, I need some graph optimization. And I sort of revamped my whole approach, because then I referenced OrbSlam, because I knew I needed to do bundle adjustments. And I had like a first iteration of bundle adjustment, but it wasn't really working well. And so therefore I referenced the orb implementation, and in slam.py is where I have my these different classes of frame, because now we introduce the ideas of keyframes, which is that because you want to build a map, and these features that you detect and you project in 3D, not all of them are useful, right? So you might also have redundant, like first you need to match them, and second, if you add all of them to the mapping thread, then you're going to overwhelm your optimizer in the backend, and there's going to be too many points, and it's going to struggle. So therefore, you only want to give it to the backend if it's useful information. And so therefore, you need to select your keyframes. And I guess the rest of it speaks for itself. So here I've implemented the tracking thread and the mapping thread. So the mapping thread does the optimization. So here, if length of cell, so when there's less than 5 keyframes, you don't do anything else. You start optimizing when you have more than 5 keyframes. So you have a set of keyframes and a set of map points that are updated in place. And I think that's pretty much it. I hope this was helpful. I don't think I did that good of a job, but at least if that answered some of the questions on how I went about this process. So this took me like months to if you look at my commit history, it took me a very long time. And I spent like a lot of time on this. And I think the reason it's so hard is not as much like implementation, but when something doesn't work, you have to debug it, right? And in such a complex system like Slam, when there are so many different moving parts, it becomes really hard. And the way I sort of slowly figured it out is you change one small thing at a time, right? So you can actually isolate the problem and figure out, like when I have my poses jumping around a lot, right? Like it's not working. Like it's not working. There could be so many reasons it's not working, right? And so you test out different hypotheses on why it's not working. Is it because my matchings are incorrect? So then you can look at your matches. And I did notice a lot of better results when I filtered out the matches. But then there comes a point where you have so few matches that your optimization cannot get a good estimate, or it can't converge as well, because you just don't have that many matchings to work with, even though each of these matchings are correct. So there's like a middle point for everything. And you only realize that there are these trade-offs when you implement it yourself, right? You're never going to be faced with these trade-offs if you just use someone else's implementation. So best of luck to you if you want to implement Slam from scratch. I hope this video was helpful, entertaining, useful, but mostly it's for educational purposes, and it's also for me to document what I did. And if you enjoyed the video, then thank you for watching. You can subscribe, and I'll make more videos like this. Thank you.